Hello everyone, I'm Yan Haojia, a PhD student from Nanyang Technological University. Now I will start to introduce our work. Imagine a scene, hearing a dog bark behind you. Instinctively turning towards the sound, you find a parked car while a silent dog stands nearby. Humans can flexibly resolve those discrepancies, but what about the AI model's performance? We investigate modality conflict and bias with sound source localization, short to SSL, which asks, where is the sound source in this scene? Next, we introduce a six-condition SSL benchmark for humans and AI. First is the congruent condition, where audio and visual cues align in both semantics and location. The second is conflicting visual cues, which semantics match but locations don't. We also introduce other experimental conditions. Please check out our paper for details. To compare AI performance with humans, we conducted a cytophysical experiment in which participants used the mouse to click on the perceived location of the sound source. Existing public audiovisual datasets are limited by bias towards centered large objects and mono-channel audio. To address these limitations, we develop a scalable method to generate two-channel stereo audio for static images, use 3D simulation engines, enabling the creation of diverse, naturalistic, and spatially grounded audiovisual datasets. First, we filter a subset of high-quality audiovisual pairs from public datasets, then place the receiver and the speaker in Unity. Following, we use the depth anything model to estimate the scene path and the 3D coordinates to accurately locate objects within the simulated space. Finally, we apply the Steam audio listener in Unity to simulate spatial processing in the pinna of human ears with stereo audio use head-related transfer function HRTF filtering. To tackle SSL, seeking inspiration from neuroscience, we propose our EcoPing model based on the standard audiovisual model architecture. EcoPing gets the image stereo audio input, applies the pinna filtering, and converts to cochlear representations. The downstream encoders process the image and the cochleogram independently to extract their phase maps. Finally, we used the cosine similarity to compute the visual and audio similarity as indicated by the heat map. The location with the highest activation value indicated by the triangle is the predicted sound source location. During training, we use contrastive learning to align the semantics of auditory and visual inputs. And we also use the sound source localization loss to learn the spatial cues. At inference, we introduce the AACC to evaluate different models' SSL performance. If the peak activation from the heat map falls within the bounding box of the sounding objects, we think the AACC is 1, otherwise it's 0. We evaluate the model performance on all 6 conditions and compare our EcoPing with current SOTA method S3. For congruent condition, object size matters for humans and AI models. Larger sounding objects are easier for humans to localize. Only humans and EcoPing maintain consistently strong performance across all object size, including small objects, whereas IS3 does not. IS3 underperform EcoPing because IS3 is trained on unbalanced dataset. In contrast, EcoPing is trained on our AudioCoco dataset, which offers greater diversity in the size of sounding objects and their spatial locations. For more result analysis on other experimental conditions, please check out our paper for details. In conclusion, we examine modality bias and conflict resolution in SSL across humans and AI models. To tackle this problem, we also leverage 3D simulation environments to generate the AudioCoco dataset and propose our neuroscience-inspired model EcoPing. We support open science. Please check our website for papers, code, and data.